Good morning. Can everyone hear me okay? Good. So I'm going to be talking about a topic which is the networking and tasking of distributed spectrum assets. So when one has low-cost devices, right, and a lot of them out in the field, you have to network them together and make them work cooperatively together in order to achieve the results that you'd like to get. Thank you. So by way of overview, I'll talk a little bit about the problem being addressed, what are the key challenges that we see, and really those key challenges are really four major areas that I'm going to discuss today. One is the distributed discovery of assets. And what that means is when you have a large set of assets out that you're trying to use, they may not be your assets, and it may not be a controlled environment. So how do you find out what's out there and what the capabilities of these assets are, so you can figure out which ones you need for the job at hand. The other topic is the autonomous tasking of assets. So there the issue is, okay, I have things that I want to make work together. How do I do it in an automated way, because I can't go out and manually set things up on each individual node. That would become non-scalable, really. What is the resource impact? So when I task these assets and get them to do certain things, they're going to consume resources. In particular, they're going to consume communication resources, and that may impact the assets that are out there. And then finally, there's this whole question of scalability. What happens when the network gets very big? How do you manage it in such a way that the overhead of the network itself doesn't swamp what it is you're trying to do? And then we'll talk about some of the lessons learned in what we've done so far. So what is the problem being addressed? Existing spectrum monitoring techniques typically rely on high capability devices, expensive devices, powerful devices that are deployed sparsely. Now, as we've seen, and I guess it's a theme of this symposium today, there are new situations emerging. There are the possibility of deploying really dense networks of lower cost devices. Now, when you have lower cost devices, you're going to have a lot more of them. So these low cost devices have got significant capabilities, and we've already heard about some of those capabilities earlier today, both with respect to RF capabilities, that is the transmission and reception, and also with respect to processing. So once you have a whole bunch of these lower cost devices, the utility of them and the RF capabilities that you can synthesize can be greatly improved by coordinating these devices. But in order to coordinate these devices, you need some kind of distributed application model. And the model that we've been thinking about and that other folks have been thinking about is similar to the app model. It's similar to the model where you have what you have on your smartphones. So the idea is that you have a spectrum app that runs on your phone in a sense, except it's not your phone necessarily. It could be one of these distributed assets. But the key point there is that this is in some sense, a secondary application. It's not the sole purpose of the device is out there is not to run your app. It has a primary mission, if you will. What you're doing with spectrum sensing might be a secondary activity. So how do you manage that in such a way that you don't impact the primary mission of the device? And one of the things that is necessary to make that work is to make sure that the coordination function has low impact. and there's very little overhead, as little as possible. So here's a typical use case one might consider. You have a network of assets. They actually have the ability to communicate with each other a priori. So the notion is that it's, in some sense, what we're doing here is overlaying on top of a network of existing assets. So what are we overlaying? Well, we are instantiating little bits of software on some of the devices that enable us to run Spectrum applications, and the coordinating function or the coordinating application, what that needs to do is firstly identify which assets are out there that can be used. So that we call that function discovery. So the application has to, in some sense, query the network and find out what is out there, what are the capabilities, and are they available. Once the application knows that, it can then go about actually tasking the nodes. So the tasking function would be that one of the nodes inside the software is a tasking function, and this node here would consider the set of nodes in its neighborhood that, and in respect to a particular type of RF application, say, okay, which of these nodes am I going to actually task, and how am I actually going to allocate the work across each node? Because the nodes may, in some sense, have different capabilities. They may be busy doing different things, and the job itself needs to be properly allocated across these nodes. So once that is done, then you can actually start running the RF application. That would generate some activity. Once the activity is complete, there would be a sort of measurement process that would be invoked. It actually might be invoked while the activity is going on. And then the measurements would be sent back, ultimately back to the application. So that's the typical use case that we're looking at. And the distributed application lifecycle really looks like this. So what this means is on each of these nodes, right, there's this piece of software is sitting there, and it's doing what we are showing over here. So there's a job queue, and it starts to read the job queue. And of course, if there's nothing in the job queue, it just sits there waiting. But once there's something in the job queue, it identifies the job and then figures out which nodes are the ones to use, what are the capabilities and availability of the potential nodes. Once it has a set of nodes that can actually potentially execute the job, it needs to decompose the job into individual pieces, individual tasks, and those tasks could be, the task could be, for example, I want to scan the spectrum between 400 meg and 2 gig, but maybe the entities themselves are not capable of doing that whole scanning job themselves, so you have to break it into pieces, and each individual node might be scanning a sub-portion of that spectrum, or they might be scanning a sub-portion in that spectrum in a specific region. So that's an example of how you might decompose, in a very simple example of how you would break down a job into individual tasks and allocate those tasks to individual nodes. And then you run the task on the remote nodes, collect the results of the task. Now, some of these tasks may actually fail because in an environment where you are using a device that has a primary mission, if you will, when that mission is activated, your task may fail. So you might think about it if you're using your smartphone, right, and you're listening to music, and then the phone rings. At that point, the audio device that you were using becomes taken over by the primary mission of your smartphone, which is to communicate. So at that point, your audio task kind of stops, at least. So that's the analogy of what we're describing over here. To compensate for this, you might have to over-allocate. So if you have some a priori knowledge of what the likelihoods are that tasks may fail, you can over-allocate you can allocate more nodes to do the job than you might need in an ideal world, and that way compensate for the fact that tests may fail. Once the results are obtained from the individual nodes, you collect these results, combine them. You might have to fuse the data and determine the result, and then you know you've got a result, and it may be sufficient or it may not. But in some sense, this is the life cycle. So we try to describe a problem here, and it's clearly a problem that has a lot of synergistic other problem areas. That there are other related problems. So one related problem is the problem of spectrum infrastructure. So spectrum infrastructure is about having a mechanism to convey information about the spectrum and instructions on how to implement spectrum capabilities, and clearly that has a distributed aspect to it. Another area that's synergistic is wireless distributed computing. So we all know about distributed computing. Wireless distributed computing is doing distributed computing in a wireless environment. That also has that same distributed facet to it, and the wireless environment is actually a key constraint, because that actually really dictates the type of communication, storage, and other algorithms that you need to use to make things work in this environment. And then, of course, there's the whole area of spectrum applications. You know, there are many spectrum applications. I just listed a few of them here, but there's spectrum mapping. That's mapping out the RF spectrum in space so that you know exactly what frequencies are being used where. Distributed sensing, direction finding, geolocation, that means identifying where objects or emitters are. Coordinated jamming. So if you need to suppress a certain signal, you can actually do that through in a coordinated, more surgical fashion, as opposed to just dumping large amounts of power, which actually may not be feasible in some of these new environments. And then finally, distributed MIMO. So out of this work, there are a number of problems that we think are key research problems that need to be solved in order to make progress here. So one of the problems is how to form an efficient distributed computing network when you've got mobile nodes, when the nodes are heterogeneous, they're different from one another, and similarly for the links, you have different modulations, different types of link protocols. How do you actually make this distributed network work and work efficiently? The next problem is, and I'm going to say a little bit about each one of these problems, without going into a great deal of depth in each one. So the next one is how to model resource usage in a general fashion across heterogeneous devices, right? So again, we've got different kinds of devices. People are creating new ones all the time. But if you need to do task allocation and resource modeling, you have to have a sort of abstract way of modeling resources that's going to work across these different devices, so that you can use that information in allocating tasks. Next problem is how can the workload be optimally distributed among a set of nodes subject to complex constraints? So there is a sort of optimization problem here. It's like, okay, I've got a certain amount of resources, I've got a job to do, I have a metric. I mean, maybe metric is the number, right? Maybe it's minimize the actual resources used. But I've got a lot of complex constraints. The nodes have different capabilities. They are timing constraints. The job may need to be done in a certain amount of time. I've got 10 seconds to do it. I have, spatial constraints. So the problem becomes a difficult optimization problem because of the fact that we have these very complex constraints and an uncertain environment. And then the next key problem is how to model information value and preserve it while disseminating data. Actually, this is a topic that we're collaborating with WINLAB, in fact, with Wade back there. But the idea is once I've generated information, right, some of it is more important than others. Some of it is time critical, others may be less time critical. How do I model that? Right? How do I model the fact that the information is different, and how do I, and the fact that it may actually change over time, and how do I preserve that notion while disseminating this information, which means that I need to prioritize the dissemination so that the most important data at a given point in time gets priority, right? And what is most important at a given point in time will depend on many things, including what time it is. So it's also a difficult problem. So going back to the discovery problem, I'm going to say a little bit more about this problem now. So why do we need to do discovery again? So the attributes of nodes that are useful to applications, such as spectrum mapping or sensing, etc., differ from those in a regular IP network. So many people that have a background in networking are familiar with the concept of discovery in the context of general networking, IP networking. And what discovery means in that context is finding out nodes, address, name, and so forth. But in the case of spectrum applications, the information that an application needs to find out is not only the node's address, but it's more importantly, it's the node's capability. Is it capable of scanning, and over what spectrum? What signal processing capabilities are available? I may have to do like FFTs or something like that. Will I be able to do it on the node? And this information needs to be geotagged because the jobs that I'm doing typically have a geolocation, a geographical aspect to it. I want to do a scanning in a particular region. So I need to know about the nodes in that specific region, not necessarily just their addresses. Furthermore, some of these attributes, such as location, for example, could be very dynamic. This certainly applies to mobile nodes, and in theory could apply to nodes that are airborne nodes that are very highly mobile. So certain attributes need to be tracked and monitored and known, in a much more frequently sampled fashion than something like a static attribute, like the particular scanning capability of the node. So the way we talk about doing distributed discovery here is through a mechanism that involves registration, advertising of information, and then ultimately querying for the information. So the idea is, for scalability, we would break the nodes into different domains. I'm not going to say too much more about that, but that actually is a problem in of itself. But assuming that you've actually broken the nodes into domains, the idea that we're proposing is that nodes will register information about themselves to a local server. And that information is their capabilities, whether they're mobile or not, geographical location, etc. Once that information is initially registered, a subset of it can be shared actually among these different registration servers. So the idea is you would propagate, or you could propagate portions of this information so that it becomes more globally known. But you don't necessarily want to propagate all of this information because they're particularly not the individual node updates, because that could end up swamping the network. And then finally, when you need to find out this information, so you want to discover which nodes are out there with the capability you want in the region that you need, you issue a query to a service point, and that query may end up being propagated through the network in order to hit all the servers, or hit particularly the servers that may be associated with the region that you're interested in. And by this means, an application can discover the information about nodes. So, and why we need need to break those nodes into these clusters, right? I kind of said that it needs to be done, and this is a little bit more about why. So if you had a simple, if you had a network that had a flat structure, and you said, okay, I have a server here, and all of these nodes are going to register information about themselves to the server, and then you model this in a very simple way, what you would see is that as you increase the number of nodes, the load increases linearly. It's almost like, well, this is obvious, isn't it? Yeah. But the load would increase linearly, and of course, as the network grows, the load would become very large and might easily overwhelm the capability of the network. So the way you address that is you break the region into clusters, and then you register within the cluster, and then the load that's introduced is really down here because the number of nodes is very small, and you manage the load that is being introduced through this discovery process. And how do you form these domains? Well, there are a lot of different ways to do that. I'm going to just give you one example here. There are techniques there are so-called clustering or domain formation techniques. The idea is that these are sort of self-forming domains. So in order for self-forming domains to work, typically nodes have to emit some information. So there's a notion of nodes are emitting beacons, and based on the information that is in the beacon, you can propagate some of that information in your own beacon. So that you don't propagate the beacons, you just send out your own beacon, but you modulate your own beacon by what you're hearing in your environment. And for example, if you have a ordering on the nodes, you can propagate some of that ordering information down the network, and thereby essentially cluster the node. So you propagate the ID of the highest priority node up to a certain hop count, and that would define one cluster. And similarly, you would do that for other clusters. And because you have this protocol is dynamic, if the key nodes that are in some sense, the root or leader nodes in each cluster, if they disappear, if they become unavailable, break, or disconnected, then the nodes will stop hearing their beacons and then would change the information that's being propagated, and then the clusters would reform as needed. So the nice thing about this kind of technique is that firstly it scales up the information flow by scoping the network into smaller domains. It's autonomous, it's dynamic, it supports splits and mergers. That's a big problem obviously in mobile networks, and it's very robust to loss of information. Loss of information about links and nodes and with respect to node movement. And this is just another, I think a very simple chart, but the idea is that this is about managing the registration information generated by this technique, and the idea is of this particular chart is to show that actually you can maintain this information within a cluster for a very small amount of bandwidth. This is very important because there are networks in which this bandwidth is a very scarce resource, particularly in mobile networks. Okay, so the next problem I want to talk about is the problem of resource availability model. So now this refers to the nodes themselves that you need to task. These are the RF devices that are going to run the things that you actually want them to run. They have multiple subsystems. They have computation subsystems, they have processors, they have communication, RF subsystems, there's memory, there's storage, there's power. All of these subsystems need to be modeled because they impact the availability of this resource for the job at hand. If you have tons of computation, communication, etc., but the battery is about to die, well, then it's not really available. So we need to look at some of the metrics associated with these subsystems such as power, energy, CPU utilization, bandwidth, and latency, and then incorporate that into availability model. So here's an example of how one might do this. So you have a list of resources, right? Receiver, transmitter, processing, memory, communication, and battery. And then associated with a particular task that you want the node to accomplish is a demand on each one of these resources. Now these are just made up numbers, but the idea is that this is a model of the demand. Then similarly, you have the resources themselves, and they have an availability because they're busy doing other things or otherwise engaged, and this is the availability of those resources at this particular point in time. If you compare the demand with the availability, you can see which resources can be satisfied and which ones might not be satisfied. And in fact, this tells you whether or not this particular node is available for the task. So the idea is one can form fairly complex models, right? Or one can form very simple models. I think at this point, simple models are the way to go. In fact, the way we've been doing this is we come up with a single parameter based on all of these input parameters, which is like a parameter of a probability value. Is it available or not, and what's the probability? And the tasking algorithm uses this information to decide on whether or not to allocate a node. So if the probability that the node is available is close to 1, that means, yes, let's use this one. If it's close to 0, it means avoid this node, don't use it. That's likely to not be able to actually complete. So this is just a very simple example of the kinds of things one has to do to address this aspect of the problem. Other problem that is very extremely important is the tasking problem. Okay, so this deals with you've got autonomous operations here. You want your nodes to sort of, in some sense, operate autonomously. Figure out which nodes get to do what. You want that done independently of operator control. So the problem is, okay, I've got a set of interdependent tasks. Interdependency because you might have to scan before you fuse, right? And I've got a set of n nodes that are available to do this. How do I map these interdependent tasks onto the set of n nodes, subject to all of these diverse constraints on the resource constraints that we talked about, the timing constraints, and so forth, and while optimizing some desirable objective. So the constraints include timing constraints, like the job needs to be completed in less than a few seconds or less than X seconds. The resource constraints, constraints on the bandwidth, processing, memory utilization, etc. There's also the uncertainty. We need to model the uncertainty because it's not deterministic here. There's uncertainty both in communications, which means that if I issue a command, will it actually get there? Or if the task executes and issues a report, will I actually receive it? These networks have imperfect reliability. Also, the uncertainty in task outcomes. As mentioned, if I have some notion of the probability that a task may execute, it's not 1 or 0, it may be something in between. So how do I deal with that? Also, we have objectives. Okay, so the objectives are, okay, I've got these constraints, but I also have objectives. I want to maximize the coverage. I want to maximize the amount of spectrum I can cover with my resources. I want to maximize the size of the region that I can cover with my resources. Or I have to actually cover a certain region and spectrum. How do I do it in such a way that I minimize my resource consumption? I don't want to use twice as many nodes as I actually have to. Other people might want to use those nodes. Another type of objective might be to say, okay, I've got a certain amount of resources available. How many tasks can I run? Maybe if I organize things differently, if I do for example, the shortest job first, that's better than doing the longest job first. And if I schedule the jobs appropriately, I'll end up being able to complete more tasks with one strategy than with another strategy. So how do I find the best strategy in that regard? And then another optimization is I might have a single job and I want to minimize the resource usage. So these are hard problems, actually. With all of these constraints, then actually it's a very hard problem. Classical optimization techniques generally wouldn't really apply here because you'd have a state space explosion due to all of the constraints. And they also don't handle uncertainty very well. There are distributed constraint optimization techniques, but again, they also have exponential runtimes and would become difficult. Markup decision processes handle uncertainty well, but they don't scale well in this particular case, again, because of the nature of these constraints. So the technique that we have been using is based on constraint-based search. And it's quite appropriate here, we feel, because it's inherently incremental. It can be extended to handle uncertainty very easily, and it's well suited to these dynamic domains. So a little bit more about what we've, an example of such a task and what we found. So let's consider an example of a coverage task. So in this task is one where we want to sense over some designated dimension, such as geographic region or frequency range. And here's an example of where we're actually trying to scan a geographic region. So the idea is that we have multiple devices that are deployed here. Right? Each device has a range, an effective sensing range. Right? And we can select which devices can be used to perform this task such that we cover the entire region while minimizing the number of required nodes. So the basic strategy is really a minimum set coverage procedure, and there may be optional tasks that are associated with this, such as fusing the results of this information. This is actually again a hard problem. It's NP hard, but we can actually get results using the search-based techniques. So one thing that we found with the results here is that you never really get perfect coverage because of the non-zero task of a task not completing. And the way we formulated this particular problem was not to sort of oversubscribe. So if you're trying to sort of minimize the number of nodes, we found we could get close to perfect coverage, but probabilistically, right? It's not perfect. The second thing is that taking into account the awareness of the node availability. So this resource model that tells us that with some learning, right, we learn something about the availability of nodes in the environment. That actually is extremely valuable and makes a big difference than just randomly assigning nodes. So this is actually a very important result because in a real system, you are going to be limited with your resources. And what this is telling us is that intelligence in managing this task allocation makes a big difference. And when I say big, it was like 30%, which in terms of resources is actually a lot. Okay, the next problem I wanted to discuss a little bit about is the problem of modeling information value. So the problem here again is firstly, the volume of data that needs to be shared in this environment, right? You may exceed the delivery capacity of the network. So certainly if you scan and you generate lots of spectrum information, it's easy to see that could be very large and you just might not be able to disseminate it in that form. So without going too much more into that aspect of the problem, we'll just say this. If the resources are limited, priority should go to the information that adds the greatest usefulness to the application at this point in time. So Utility can be considered as a assessment of the value of data in terms of the contribution to the application in terms of some metrics. So there are different forms of this, right? So let's take an example. Let's take a spectrum mapping application, right? So prioritization can be linked to the difference in entropy, which means the sort of newness of the information. So if you're measuring something, right, and the next measurement is very different from the previous one, that has high entropy and therefore it's very important. If the next measurement is not very different from the current measurement, then it has low value and maybe much less important, and you can afford to prioritize that at a lower priority. Furthermore, as time progresses, right, if you're doing this scanning application, if you happen to scan some data and it's buried in the system somewhere, it's getting stale. And the longer it sits there, the staler it gets. So in some sense, the priority of that information should then decline with time, because even though it was once very important, it's no longer that important anymore. So there are different ways of trying to solve this problem. This is just a simple example of where we might have how you could model this information value. I'm showing here a slightly different application. It's a tracking application. You're trying to track a location. There's a device sending out coordinate information. Maybe it's being tracked by some RF sensors, for example, or maybe it's emitting its own coordinates. As this information goes through the network, you can compare what your perception of what the location is with the, if you have a priori knowledge, you can compare it with the actual, and then you can determine the accuracy and latency. Accuracy means how close it is, and latency means how long it's taking the information to get to you, right? And that allows you, by means of these metrics, to assess which information is actually the most important. So having gone through this exercise, we can come up with some heuristics here about the priority being proportional to the conditional entropy, and also inversely proportional to time. And then when we actually ran some, ran experiments on this, we found that we can show that as the value of the information is high, the probability of dropping was very low, and as the value of information was lower, then we tended to drop it much more readily. So this was a nice way of actually modeling the value of the information. So I'm going to summarize now. There are many challenging problems in this area. This notion, this model of a loner host, right, that it's not necessarily your own device that you're using, plus the network constraints, necessitate specialized protocols and approaches optimized for low bandwidth and system impact. Dynamic partitioning of the system, domain management is very important for scale to keep the overhead down. Generic resource models for heterogeneous devices are required, and learning, the availability model that we talked about, I think learning system would be very helpful. So you can measure the availability of nodes if you have no a priori knowledge, right? You don't know in advance, but after a while you'll start to see which nodes are more available, and thereby you learn that information and use it going forward. The task optimization is a key area here, and it's necessary to minimize or optimize resource usage. And as we just discussed, the model and prioritize information according to its utility. And I think that's pretty much what I had for today. Be happy to entertain any questions if there are any.